A new material is now present in the soil, marking the beginning of a profound alteration to our planet's chemistry. It was initiated not by a terrestrial process, but by the arrival of an extraterrestrial visitor. The asteroid's impact was not a cataclysmic explosion, but a quiet, localized geological transformation. The bulk of the asteroid's mass and its unique elemental cargo has been injected directly into the crust, mixing its fragments with terrestrial materials and creating a new type of geological breccia across the crater floor. Before the asteroid's arrival, Earth's chemistry was a closed system, a finite collection of 92 naturally occurring elements. Every substance, every mineral, every living organism was constructed from this limited but versatile palette. The distribution of these elements is far from uniform. Oxygen, silicon, gold, platinum. This scarcity is a fundamental constraint on our technological capabilities. The entire history of human industry can be viewed as a quest to find, extract, manipulate these elements to our advantage. The availability of specific materials has dictated the course of civilizations: Bronze Age, Silicon Age. The process of resource extraction is governed by geological and economic realities. We mine elements where they are found in economically viable concentrations, known as ore deposits. These deposits are the result of billions of years of geological processes, volcanic activity. We cannot create elements, we can only harvest them from where nature has placed them. This limitation means for critical applications we face constant supply challenges. Our technological progress has always been tethered to this known set of elemental properties. The capabilities of our batteries are limited by the electrochemical potential of lithium, the speed of our computer chips, by the properties of silicon. Scientists work to push these materials to their limits, but they are ultimately working with the same fundamental ingredients. Our pre-asteroid world was constrained by the environmental cost of mining. The pursuit of rarer elements meant processing vast volumes of ore, a constant trade-off between technology and ecology. The post-impact era begins with intense scientific investigation. Geologists descend upon the crater, using ground-penetrating radar and core samples to map the deposit's scale and depth. Simultaneously, a rigorous contamination assessment begins, analyzing air, soil, and water to understand the new element's mobility and toxicology. Microorganisms for preliminary biological readings. Test results set initial safety protocols for personnel and shape the long-term environmental monitoring plan. With core samples secured, characterization of the new element begins. Small, pure samples, xenidium, are isolated in specialist metallurgical labs. Physicists run a battery of tests to find fundamental characteristics: density, melting point, crystal structure, electrical conductivity, thermal conductivity. Chemists probe reactivity by exposing samples to acids, bases, oxidizing agents. This foundational research is methodical and slow, but essential. Each data point builds a manual of xenidium's behavior. The first practical tests are small in scale, but immense in implication. Materials scientists create simple alloys, mixing xenidium with aluminum, steel, titanium. They test alloys for changes in strength, hardness, corrosion resistance. Electronics engineers try incorporating xenidium into simple circuits to test semiconductor properties. Section 4. Cascading consequences. The discovery that xenidium can store and discharge energy with almost zero degradation triggers a cascade of impacts. Companies in battery manufacturing, consumer electronics, and electric vehicles recognize its transformative potential, starting a race to design a new generation of batteries, radically smaller, longer lasting, and more powerful. Global markets react with volatility. The value of companies with exploration rights soars, while stocks for lithium and cobalt miners may downturn. Governments see a strategic imperative to secure a supply chain for future energy independence. The discovery reshapes the geopolitical landscape. The nation where the asteroid landed now holds immense leverage, becoming the sole proprietor of a resource that could redefine the global energy economy. As other countries engage in intense diplomacy for access, the environmental implications also scale up dramatically. The central question is no longer just local contamination, but the global life cycle of the new element, from extraction to disposal. Establishing a safe pathway becomes a massive scientific and regulatory challenge, creating a potential bottleneck that could temper the geopolitical rush. Section 5. The New Equilibrium. Years after the discovery, the world settles into a new equilibrium, defined by a steady flow of xenidium. A large automated mine feeds a stable global supply chain. The most profound shift is in energy and transportation. Xenidium-powered batteries are now the industry standard. Electric vehicles now possess ranges exceeding 1,000 kilometers and recharge in minutes, rapidly phasing out combustion engines. On the grid, massive battery arrays store solar and wind energy for days, solving intermittency and accelerating the transition to renewables. This industrial transformation created new economic winners and losers. Nations who invested early in xenidium now dominate markets, while regions reliant on fossil fuels or older battery materials face decline. The global economy has been recentered, a significant redistribution of power. And while this dramatically reduced carbon emissions, a new environmental challenge has emerged: recycling the first generation of xenidium products. Section 6. Security, Law, and Built-in Delays. Xenidium's immense strategic value necessitates a robust legal and security framework. The government declares the site a national strategic resource area, placing it under direct military protection. Strict export controls are enacted, limiting sales to approved nations under conditions that prevent stockpiling or weaponization. These rules create a predictable but highly controlled market, slowing widespread global adoption. From discovery to the first commercial shipment of xenidium takes at least 8 to 10 years. This built-in delay provides a crucial buffer for industries to adapt. But the economics of extraction are also a limiting factor. Found in trace concentrations, tons of rock must be processed for a single kilogram. This cost sets a baseline price, dictating if it's viable for mass-market products like car batteries or only niche applications. Uncertainty about long-term performance also remains a constant companion. Section 7. Conclusion. Unanswered questions in a changed world. We have reached a new, relatively stable state, a world reconfigured by the chemistry of a single space rock. The flow of xenidium has created new industries. The flow of xenidium shifted global economic power, and it accelerated our transition away from a carbon-based energy system. The changes have been profound, but they have also been gradual, metered by the unyielding realities of geology, engineering, law, and economics. The path from the initial impact to the current equilibrium was not a single event, but a chain of mechanisms, incentives, and thresholds. Each step, from the first spectral analysis to the construction of a global supply chain, was a measurable process with inherent delays that prevented the system from spiraling into chaos. The arrival of xenidium has permanently altered our planet, and its long-term consequences will unfold for centuries. Now a permanent part of our environment, its accumulation represents a planetary-scale experiment whose outcome remains unknown. This event is a tangible reminder that we exist in an open cosmos. The asteroid was a random event, but its consequences have been shaped entirely by human choices, our science, our economic systems, and our priorities. We have successfully harnessed a new piece of the universe for our own technological advancement. The initial questions about the element's properties and potential have been answered, but they have been replaced by deeper, more philosophical inquiries about our role as stewards of a planet that is no longer chemically isolated. And so, we are left with open questions that will define the future of this new era. Now that we know that such elemental diversity exists in the cosmos, will we begin a new age of exploration, actively searching for other asteroids with novel chemistries? Having seen the immense economic and strategic power that comes from controlling a unique resource, how will humanity govern future discoveries of this magnitude? Will it lead to greater cooperation or to a new and more intense form of conflict? The arrival of one rock changed our world. What happens when we find the next one? What scenario should we explore next? Share your ideas below. You've been watching Ifverse, where imagination meets possibility.